All right, today we're cracking the code, the secret language that lets our software talk to our hardware. We're going right down to the metal to see how this whole thing actually works. So let me ask you this. What is the native language of a computer? I mean, it's not Python, right? It's not C++, and it's for sure not English. No, deep down, at its very, very core, a computer speaks a language that's, well, it's incredibly simple, super direct, and way more fundamental than you might think.
Okay, so here's our game plan. First, we're going to figure out what this secret language even is. Then we'll meet a real classic, the Intel 8085, and learn its basic commands. After that, we'll see how those simple commands build real logic, and finally, we'll connect it all back to the super powerful computers we've got today. Sound good? Let's get into it.
All right, first up, the CPU secret language. Let's talk about how software really commands hardware.
You know, the best way to think about this is a CPU's language isn't some huge dictionary. It's more like a dog that only knows a few commands, like fetch, sit, stay. That's it. The CPU doesn't understand the meaning, not really. It just executes these super simple actions flawlessly and at an unbelievable speed.
Now, the official term for this list of commands is the instruction set. And this is the part you really got to get. It's the complete, totally fixed vocabulary for that one piece of hardware. Every single program you've ever run, no matter how ridiculously complex, it all gets boiled down into a sequence of these basic, fundamental instructions.
Okay, to make this feel real, we need an example, right? So let's fire up the time machine and meet a true legend of hardware, one that can teach us pretty much everything we need to know. The Intel 8085. So, you might be asking, why on earth are we digging up a chip from the 70s? Well, it's simple. Its simplicity is actually its biggest strength for learning this stuff. See, the 8085 has all the key ingredients of a modern CPU, just without the billions of extra layers of complexity piled on top. If you can understand how this little guy works, you'll understand the core of every processor, even the one that's in your phone right this second.
And just to put that simplicity into perspective, get a load of this number. The Intel 8085 was built with around 6,500 transistors. That's it. Now burn that number into your brain, because we're going to come back to it later. And trust me, the comparison is absolutely going to blow your mind. All right, let's get into the nitty-gritty. Let's look at the basic building blocks, the actual vocabulary of the 8085. So, the 8085's entire vocabulary, its whole set of words, fits into just 5 basic groups. The easiest way to think about them is as verbs, action words. You've got commands for moving data, commands for doing math, some for handling logic and making decisions, others for branching to new places, and finally a few just to control the machine itself. Let's check out a couple of these in action.
Honestly, the most basic operations are almost funny in how simple they are. Take move A, B. All that means is move what's in spot B over to spot A. That's it. It's kind of like telling the CPU, hey, take that number from your right pocket and put it in your left. Or look at LDA 2050. That's just go find whatever's at memory address 2050 and load it up for me. It's really just like grabbing a specific book off a massive library shelf. At the end of the day, it's all about moving stuff around.
Okay, so once we can move data around, now we can start doing some math. An instruction like add B, well, it just tells the processor to add the value in B to whatever is in A. And here's the beautiful part. All that super complex math, from crunching numbers in a spreadsheet to rendering an entire video game world, it's all just built from millions and millions of these tiny, simple steps. It gets even simpler. INR-A just means add 1 to A. Seriously, that's it. It's the digital version of just taking one small step forward.
Okay, so now we know some of the words in this language. Let's see how we can start stringing them together, combining these simple commands to build much more complex things, like logic and loops.
So, have you ever wondered how a computer actually makes a decision? The secret is that it doesn't. Not like a human does, anyway. There's no intelligence here. All it does is a super simple comparison, and then, based on the result of that comparison, it either continues on or it jumps to a different part of the program. It's 100% mechanical.
Let's actually peek under the hood and see how a simple if statement works. It's like a little 3-step dance. First, the CMPB instruction compares two values, A and B. It basically does a quick subtraction to see what the result is. Then, and this is the magic moment, the JZ address instruction asks a question. Hey, was the result of that comparison 0? Or, in plain English, were A and B the same? If the answer is yep, the processor jumps to a completely different spot in the program. If the answer is nope, it just carries on to the very next line. And that's it. A simple comparison and a jump. That right there is the foundation of all decision-making in every computer ever.
All right, let's pull back and look at the big picture, from 8 bits to today. So why does learning about this, 40-plus-year-old chip still matter so much?
It really all boils down to this one single, powerful idea. The fundamental principles haven't changed at all. Only the scale has.
Okay, you remember that number I told you to burn into your brain? 6,500 transistors? Now, look at the jump. From about 6,500 transistors to billions of them. From a vocabulary of just 74 simple instructions to literally thousands of them. We went from handling tiny 8-bit pieces of data to giant 64-bit chunks. The difference in power it's just astronomical. But the DNA, those core ideas of move, add, and jump, they are still exactly the same.
So I'm going to leave you with this to chew on. The 8085, it built the entire early world of computing on just 74 simple commands. The processor in your phone has thousands. We've obviously gained an incredible amount of speed and power, but have we lost anything in the process? Maybe a certain simplicity, an elegance, or maybe just an understanding of what's really going on deep inside the machine? Definitely something to think about.